Hello and welcome you all to the 19th lecture of the NPTEL course Electroweak Interactions in the Standard Model of Particle Physics. And in today's lecture, we are actually going to provide a new concept. I am going to give you the main idea behind the quantization principle of quantum field theory, and this is what is called the canonical quantization. So, let us get started. So, what we sort of assume or understand is that universe consists of different yet indistinguishable particles which are created or destroyed by the interactions, and in this quantum field theory the particles that are there are essentially described by the excitations of some quantum fields. Now, the way that we do this is to basically conceptualize first the particles with respect to the classical fields, and then do this canonical quantization by which we can render the quantum properties to them, and then they can describe as particles, and this is what the process of canonical quantization is. Okay. So, if I want to kind of describe the methodology through which this canonical quantization is done, the step 1 of this process is to first construct the classical Lagrangian or Lagrangian density L. Now, this is something which we are already familiar with. Say for example, if you have to go back and look into the Lagrangian which is actually for the Dirac particles are, can you tell me? So, this will be psi bar I gamma mu del mu psi minus m psi bar psi. So, this is essentially where psi is basically the fermionic fields with which we have constituted or constructed what we call the classical Lagrangian. Now, the second step is essentially to calculate the momentum density pi, and from that momentum density pi we can construct something called pi naught, and then we can actually form the Hamiltonian H. Okay. So, this is what we have to do. In this step 3, we basically now treat these fields and the momentum densities not just as fields, but rather in terms of operators. So, now we treat the fields and momentum density as operators, and we impose the commutation relations or anti-commutation relations amongst them to make them quantum. So, this is the main step of what from where we actually go beyond the classical fields and treat them as quantum fields. Okay. So, you remember that the basic quantum prescription was the step where we assume that x and p, these two are operators which do not commute, but when the commutation relation gives you something like IH cross, right. So, similarly here the fields and the corresponding momenta or momentum density, when we treat them not to commute, but rather give a non-zero commutation relation, then basically we have the quantization imposed on those fields, and thereafter in the step 4 what we do, that we expand the fields in terms of creation and annihilation operators, and basically this expansion of those fields in terms of creation and annihilation operators follows the same prescription that we actually talked at the very beginning, that basically the solution of suppose Klein-Gordon equation or the Dirac equation basically inherits both the particle and antiparticle solution, and how to create or particles destroy antiparticles, or how to annihilate particles and create antiparticles, we need to expand them in terms of this creation and annihilation operators, assuming that this creation apparatus acting on a vacuum will produce a particle state out of that. Okay. So, that is basically, and this will be in conjunction with the commutation or the anti-commutation relation of the fields and the corresponding momentum density that we have defined in the step 4. And this will allow you to use the occupation number or the particle interpretation, and therefore, we will basically then can identify the particles out of the quantum fields. In the last step, there is some step called implementation of normal ordering. Now, this is something interesting, that it turns out that we face some infinities when we are writing the Hamiltonian. You remember the whole exercise of doing this harmonic oscillator, right? So, in the harmonic oscillator, eventually what we did, that the harmonic oscillator energy was half plus h cross omega, right? So, that is exactly what we are aiming for. Now, instead of the harmonic oscillators, what we have is essentially the quantum field theory. So, let us take an example and elaborate the same, and what I am going to do, that I am going to take the simplest field theory, and that is essentially the massive scalar field theory. Now, you remember what was the Lagrangian associated with the scalar field theory of mass m. This is essentially half of del mu phi whole square minus m square phi square, correct. So, where phi defines the scalar field, phi is a real scalar field in this particular case actually. So, real scalar field, and the Lagrangian that we write is half of del mu phi whole square minus half m square phi square. Now, what exactly does it do? That when you write the Euler-Lagrange's equation of motion, the equation of motion for this Lagrangian turns out to be what you call the Klein-Gordon equation, which is box plus m square phi is equal to 0, and you also adhere to the energy momentum relation, that E square is equal to P square plus m square. So, this is basically your Klein-Gordon equation, and this Lagrangian is what is known as Klein-Gordon Lagrangian. Now, the step 2, which we did not calculate before, is to calculate the momentum density, and momentum density pi mu in this particular context will be defined by del L by del of del mu phi. So, this is basically the momentum analog of what we usually do in the classical case, right. I mean, in the classical mechanics, we define the canonical momenta, and so this is exactly an analog to that, that instead of the position, now we have the fields, and corresponding momentum density will be defined by pi mu equal to del L by del of del mu phi. Now, what this quantity is going to be? This is trivial. If you do this exercise, this is going to be del mu phi itself, right. So, this is something that we can calculate. Now, once I have pi mu, then I can actually define what is pi 0 mu, right, and pi 0 mu will be simply del phi del t. Now, I am in a position to write the Hamiltonian density. Hamiltonian density, the definition is pi 0 del 0 phi minus L. Now, if I put all this quantity, pi 0 is itself del 0 phi. So, this will be half del 0 phi whole square minus L, the Lagrangian density. Now, if I expand, this will be half of del 0 phi whole square minus half of gradient of phi whole square minus half m square phi square. So, if I do this, this will come out to be half of del 0 phi whole square plus half of gradient of phi whole square plus half m square phi square, and this is nicely arranged according to our intuition that the Hamiltonian will give me the kinetic energy plus the potential energy, right. Now, let us come to the step 3. So, we have constructed the Hamiltonian. Now, the step 3 is the main step where we assign the quantization on these fields basically, and we say that now phi x and pi x are no more operator valued fields, rather I will actually I mean these have now become operator. I will call them pi hat x, and pi x will be called pi hat x, and so these are operator valued fields. So, that is precisely what I mean to say. Okay. And following as I just said, that the quantization relation, that x p commutator equal to I h cross, we will define equal time commutator between the phi and pi 0. Okay. So, phi of t x comma pi 0 t y, the commutation relation will be is equal to I del cube of x minus y. So, this is the equal time commutation relation which is imposing the quantization condition on these fields. Okay. On the other hand, we will say that phi tx will be 0, pi 0 tx will also be equal to 0. So, this is simply like xx commutator, px commutator, these are all 0, right. So, therefore, these are trivial. So, basically this is the main point. So, this is quantizing your classical theory to a quantum theory. Now, what we are going to do, that we are going to expand the fields in terms of creation and annihilation operators. So, this is another important point that we have to do, and this allows us essentially to get the occupation number or the particle interpretation. Now, how to do this? You basically will say, now this phi x is essentially constituted of a measure which actually is integral of dq p by 2 pi whole to the power 3 by 2 into 1 by 2 e p whole to the power half, and then there is within the parenthesis two term, one is a p e to the power I p dot x and a p dagger is into e to the power minus I p dot x. Now, you see that in this expansion that I have written here so far, I have no time coordinates at all. So, I have only defined in terms of spatial function, and basically what I have done, that I have used these annihilation operators a p and this creation operators a p dagger into expand the phi x in terms of a p into e to the power I p dot x into a p dagger into e to the power minus I p dot x. And here I have defined that E p follows your the relativistic energy momentum relation, which is plus p square plus m square whole to the power half. And what are the commutation relation between the creation and annihilation operators? This is exactly like the way that we actually had it in case of harmonic oscillators. This is a p a q dagger commutator is equal to delta cube of p minus q. And this is interesting to note that if you now impose this commutation relation of a p and a q dagger like delta cube of p minus q, now put it back into the expression of phi x, and the pi 0 x can be defined just in terms of the derivative of phi x, and then basically we can find out that one can check that this leads to the equal time commutation relation that we actually defined in step 3. So, therefore, the mode expansion that we are doing for the fields with respect to this creation and annihilation operators, that is essentially in conjunction or in agreement with commutation relations that we just defined here. Okay. So, now what we can do, that we can use the time evolution of this operator in the Heisenberg picture to kind of make them time dependent. Now, this is something that we have already seen, that how the fields transform under the spatial translation or the rotation. This is something that we have envisaged. So, you can imagine that phi of t x will be defined by the time translation operator, let us call that u t 0 in the following way, that phi t x will be u dagger t 0 phi x u t 0, and then this u t 0 is nothing but e to the power I h t. So, this is something that we have e to the power minus I h t, so that u dagger t 0 is e to the power I h t. Now, the point is where exactly this e to the power I h t operator will act on phi x. Remember that phi x now has been expanded in terms of this creation and annihilation operators a p and a p dagger, right. A p is having a part of what you call the outgoing wave, and a p dagger is having the part of incoming wave. Now, the point is the only part that this u t 0 affects are the creation and annihilation operators, and one can show basically that e to the power I h t a p into e to the power minus I h t is simply e to the power minus I e p t, and on the other hand e to the power I h t a p dagger e to the power minus I h t is e to the power I e p t into a p dagger. So, this is how the relation, the time translation is going to affect. So then you say that I can actually have the time evolution of this whole phi x that I actually defined above, and now write phi x. Remember that this x is no more a spatial coordinates, this actually is t comma x. This is a 4-dimensional space time coordinate, and then what we have is nothing but that we actually append one factor of e to the power I p t or e to the power minus I p t in front of AP dagger and AP following this relation. So therefore the time translated part is going to look like AP into e to the power minus I p dot x. Remember, now this is a 4 vector, not the 3 vectors that we have. So AP into e to the power minus I p dot x plus AP dagger e to the power I p dot x, right. So this is basically your field. Now it has both space and time components in it, and so the mode expansion is looking like this. And what is the rationale of this mode expansion was, I will come back to this point once again, but you can argue that the quantization principle that we invoked by having this non-zero commutation relation between the phi x and the corresponding momenta, the conjugate momenta or momentum density, whatever that you want to call. Now that condition is satisfied using this mode expansion when we impose the that this creation and annihilation operators also commute to give you the relation like AP AQ dagger delta cube of P minus Q. So with this, basically I have a sort of, I am envisaging that I am having some particle identification which are coming up. Okay. But when I look into this measure, which is like dqp by 2 pi whole to the power 3 by t 1 by 2 p whole to the power half, this part of the measure, I mean, why exactly this looks like this is actually a question which we didn't answer before, and particularly the fact that now the field expansion has been done in a Lorentz covariant way, right. I mean, basically we have expressed this in terms of 4 space-time points. On the other hand, this the expansion, the mode expansion is also done with e to the power minus I p dot x, where p and x are essentially the 4 momenta and the 4 coordinate, and similarly here. So then the measure is dqp doesn't seem to be quite manifestly Lorentz invariant. So therefore, what we actually expect that the measure should actually be something like d4p, right, with p is the 4 momenta defined with energy and 3 momenta itself, having this relation that p square, the 4 momentum square, is e square minus p square is equal to m square, and this is precisely what is called the mass shell condition, that p square is equal to m square. Whenever the particles are physically present, then this satisfy this relativistic energy momentum relation, that p square is equal to m square. And this actually gives you basically a hyperboloid in the 4 momentum space, which I am not going into right now. But the basic point is, then we expect the integration measure of expanding the phi x should rather be in terms of d4p delta of p square minus m square into theta p 0. Now, why this del square p square minus m square? Now, this is precisely what we have seen, that this is the mass shell condition, that e square minus p vector square equal to m square. If we have to impose this energy momentum conservation relation to the particle, then this is what we require. And theta p 0 means p 0 greater than 0, which basically indicates that we are adhering to the positive mass. Okay. So, because otherwise p square equal to m square may have 2 possible roots, p equal to plus m and p equal to minus m. So, this looks like to the integration measure. Now, one can do an exercise at home, which I am not going to do here, is that the delta of p square minus m square theta p 0, you can show that this is nothing but 1 by 2 EP delta of p 0 minus EP into theta p 0. Okay. So, this factor of 1 by 2 EP which you actually see, this is essentially coming from here, and there is this additional factor of 1 by 2 pi whole cube that is essentially coming from this inverse Fourier transformation. So, that the Lorentz invariant measure is essentially coming out to be d cube p by 2 pi whole cube into 1 by 2 EP. Now, this is, if you remember, in our initial lectures also we actually encountered this phase space measure when we are actually trying to find out the density of states for the collisions or the decay processes and so on, right. So, this is essentially therefore Lorentz invariant. So, you can actually explicitly demonstrate that. Okay, but I have argued it from the point that if you also have this thing like d4 p delta of p square minus m square theta p naught, from there itself you can arrive to this quantity. Now, suppose I would like to see that how I can define a Lorentz covariant 4 momentum state, then I would like to ask this question. So, suppose if I choose this Lorentz invariant phase space factor which I just derived like d cube p by 2 pi whole cube into 2 EP, and assume that there are ket and bra of p which are arranged in this way. So, is this Lorentz covariant operator? So, suppose can I define this whole quantity as 1? Then we will actually argue that we can do it consistently. So, first let us remember that the normalization of the momentum states like p q, when you take the dot product of that is going to give you delta of p minus q. Now, remember this p and this q states are essentially the 3 momentum states. Now, let us upgrade them to the 4 momentum states, and let us define that this p is nothing but 2 pi whole to the power 3 by 2 into 2 EP whole to the power half into p vector. Now, why? So, this is my definition of the Lorentz covariant 4 momentum state. Why did I define it like this? Because you can show that with this previous definition of the operator and with this particular definition of the 4 momentum state, I can actually define the inner product of p and q to be 2 pi whole cube into 2 EP into delta cube of p minus q. And with this one you can also define the q to be consistent. So, this is what you can actually explicitly check. Now, with this definition of 4 momentum Lorentz covariant states that we have defined, I can now define the creation operators like alpha p dagger equal to 2 pi whole cube into 2 p whole to the power half into a p dagger. So, it is appropriately normalized so that they create Lorentz covariant states. Okay. So, because I have been talking about a p dagger when acts on 0 creates a 3 momentum state p state, but when you have this alpha p dagger acting on the vacuum state, this actually creates a 4 momentum state p. Okay. So, then you can argue that now with all these things put together, then if I have to find out, so phi x, the mode expansion, should in principle be the Lorentz invariant phase space measure, which is d cube p by 2 pi whole cube into 1 by 2 EP into alpha p into e to the power minus I p x plus alpha p dagger into e to the power minus I p x, because this alpha p dagger and alpha p are going to create a Lorentz covariant 4 momentum state or annihilate one. Okay. Now, the point is, if you use this definition of how alpha p dagger or alpha p is related to a p dagger and a p, then you see that these actually cancels the factor downstairs, and what you are going to left with is d cube p by 2 pi whole cube into 1 by 2 EP whole to the power half into AP into e to the power minus IPX into AP plus AP dagger into e to the power IPX, which we actually wrote. So, this whole exercise that we actually did was to show that this is a very consistent way of doing the mode expansion, which is completely Lorentz covariant. Now, let us come to the next step. So, once we have defined the mode expansion, and this is what we argued to be the way that we should do it, we have to write the Hamiltonian density. And Hamiltonian density is something that we have already talked about, that this is del 0 phi square grad of phi square plus m square phi square with a factor of half. And now, if you use the mode expansion as we have done above of phi x, which is d cube p by 2 pi whole to the power 3 by 2 to e p whole to the power half. There is a typo which I must correct. A p e to the power minus I p x plus A p dagger e to the power I p x, put it back in the Hamiltonian, then you can show that this basically comes in the form of half of d cube p A p dagger plus A p dagger A p into E p, where E p is essentially plus square root of p square plus m square. Okay. Now, you can basically rearrange this by saying that this is integral of d cube p e p to A p dagger A p plus delta cube naught. Okay. So, or this half factor may be cancelled, and you can say that this turns out to be something like d cube p e p A p dagger A p, right, plus half of delta cube 0. Okay. So, this is how exactly this thing is appearing. Now, this first part A p dagger A p is very similar to what we actually have seen already, right. I mean, in the harmonic oscillator, this is precisely what we actually have, where A p dagger A p is gives you this particle number, right, N p operator, what to say. So, this is essentially what we actually envisaged, that now it provides you a description of quantum particles. So, you started with the fields, and now upon quantization, basically your Hamiltonian describes some energy states E p with N p sitting here giving you the particle interpretation, right. But there is a trouble like this delta cube 0, which is sitting here in the second term, that is infinitely large or infinity itself, which you can say that this is a vacuum energy, and you can for the time being say that okay, I am not interested in this delta cube 0 term, they do not carry any physical meaning, but still this infinity which is hanging out makes us a bit uncomfortable, and that is what people prescribe this thing what is called the normal ordering. And in this normal ordering, basically what you prescribe is that you normal order the Hamiltonian, and that basically brings all the creation operators on the left. So, this is the prescription by which you forcefully bring all the creation operators on the left, and so therefore, you say that the normal ordered Hamiltonian for the massive scalar field theory that we have been talking about is nothing but half of d cube p A p dagger A p plus A p dagger A p into E p, and then this half factor cancels, and you simply have d cube p E p A p dagger A p, and once again A p dagger A p can be traded to this occupation number operator N p, and this describes a quantum scalar fields which has this Hamiltonian describes a set of quantum fields or with quantized momenta, whatever that you can say. So, this is basically the idea that we actually bring out the quantum description of particles out of this classical field theory that we started our discussion with. And the crucial steps that goes into this whole thing is the mode expansion that we did. So, let us look into this meaning of mode expansion once more. So, suppose if you think of what essentially we did when we say that phi x can be written in terms of d cube p by 2 pi whole to the power 3 by 2 into 2 A p whole to the power half into A p operator into e to the power minus I p x. This is essentially reflecting an incoming with E p, and you have only suppose the A p is the annihilation operator with respect to which you are doing. So, this is a Fourier expansion, but just this does not make sense, because this only encapsulates E p equal to plus p square plus m square whole to the power half, but rather we know from the solutions of the Klein-Gordon equation we have both both the positive and negative energy solutions. And so therefore, you may say that if I have to Fourier expand, in the p modes, then I should encapsulate both the positive EP mode and the negative EP mode, right, following the logic once again of the Klein-Gordon solution that we actually got. Now, we already have seen that the negative energy particle states can also be saying that these are outgoing antiparticles with positive energy, correct? So, then you can say that these field operators phi x, when we are expanding them in terms of these modes, then they will represent incoming positive EP, which is actually particle annihilation. On the other hand, they will also same time represent outgoing positive energy EP, or basically antiparticles created. So, basically therefore, what does phi x stands for? Phi x essentially therefore stands for particle annihilation or incoming positive EP states, or and outgoing positive EP states which are antiparticle creation. So, in general therefore, phi x has to be written in terms of this measure which we detailed talked about, dqp by 2 pi whole to the power 3 by 2 1 by 2 EP whole to the power half, with AP into e to the power minus IPX plus some BP dagger into e to the power IPX, where we basically say that this AP and AP dagger are the annihilation, and respect to it creates annihilates and creates particles, whereas BP and BP dagger essentially annihilates and creates antiparticle. So, I should rather write phi x which actually annihilates particle and creates antiparticle. So, this is responsible for annihilating particle, this is responsible for creating antiparticle. But in the example that we actually did here for the real scalar field theory, basically this particle and antiparticles are the same, because we do not have any distinction, right. The antiparticle is essentially the charge conjugation, but there is no meaning of charge conjugation, the field itself is the charge conjugated state. So, therefore, we have the BP and AP the same. So, this is the reason why you have the mode expansion for the real phi as AP e to the power minus IPX plus AP dagger into e to the power IPX, and we nicely create a normalized Hamiltonian which is essentially a quantum description of a set of quantum scalar particles essentially. So, this is basically the idea of canonical quantization, or how you can visualize the particles or the antiparticles coming or describing your universe via this kind of quantum field theory. So, we will take up this exercise a little more to talk about the Dirac fields and the electromagnetic fields briefly. I am not going to do any calculations, so that the discussions that we are going to do later becomes very clear to you. Okay? So, with this, let us finish today, and I am going to see you in the next class. Stay tuned and thank you.